This is a video for AQA Further Pure Mathematics, Sequences and Series, Section 4.2, the General Maclaurin Series. We've seen already the idea that a function f of x can be approximated by a polynomial of the form a plus bx plus cx squared, etc., where we find the coefficients by making sure that the polynomial and the function agree at x equal to 0. So we find the value of the function, first derivative, second derivative, and so on. Now we can generalize this with the following function and say that f of x is equal to f of 0 plus f dash 0 over 1 factorial plus f double dash, the second derivative, over 2 factorial, x squared, etc. So that we have a general term fr, which is indicating the rth derivative, evaluated at 0, so fr of 0, r factorial on the bottom line, x to the power r. And this is our polynomial approximation. It carries on indefinitely, so we can go up to whatever power of x we desire, and it's known as a Maclaurin series for f of x. So we can use it to approximate functions provided we can work out the values of all of the derivatives. And if it converges, this is going to converge to f of x. So we've seen previously that some Maclaurin series are only valid for a certain range of values of x. Well, previous videos have used this to work out the Maclaurin series for a range of standard functions. But as long as we can evaluate these derivatives at 0, then we can use it for any function we like. So let's consider then using it for f of x, which is cos 2x. So what we need to do is to evaluate the derivatives. We can see here we've got the function, first derivative, second derivative, etc. in our general Maclaurin series. So if f of x is cos 2x, then obviously f dashed x is negative 2 sine 2x. And then if we differentiate that again, we're going to get negative 4 cos 2x. And then again, the third derivative multiplying is going to multiply by 2, negative 2 sine x. So we end up with 8 sine 2x. And then the next one will be multiplied by 2 again, giving 16, this time cos 2x, etc. Now, substituting the value 0 to calculate f of 0, f dash 0, etc. Then sine of 0 is 0, so that one must be 0. Cos of 0 is 1, so this is negative 4. This one then becomes 0 again because it's sine 2x, so sine of 0 is 0. Next one, 16. So from our table we can see that the odd derivatives, i.e. the first, the third, and so on, the fifth derivative, these are all going to be equal to 0. So it's only the even derivatives, and therefore the even powers of x which are going to have some value. So substituting then what we know into the general formula, we've got f of 0, which is 1, and then we want plus f dash 0, negative 4, multiplied by x squared and divided by 2 factorial. The third one is going to be 0, so we jump to the fourth one, which will therefore be 16, and then x to the power 4 divided by 4 factorial. We can simplify these expressions to be 1. The next one is negative 1/2, so we've got, beg your pardon, negative 2. Negative 4 divided by 2, negative 2x squared. And then 16 over 4 factorial. 4 factorial is 4 multiplied by 3 multiplied by 2. So we end up with 2 over 3 x to the power 4. Well, to work out the general term, if we examine what's going on in the table, we can see that each time we differentiate, we're either multiplying by 2 or negative 2. So it's multiply by 2, this one here by negative 2. So as we jump down each section where we've got a value which is non-zero, we must be multiplying in total by negative 4. So going from this one to this one, we've multiplied by negative 4, and then from this one to this one, multiplied by negative 4. So this will be negative 64, and the next one again would be negative 4 multiplied by that. So putting that into the functions that have been evaluated at 0, then we get negative 64 here. So these are all powers of negative 4. We've got negative 4 to the power 0, negative 4 to the power 1, negative 4 squared, negative 4 cubed. And those are for the derivatives which are the second derivative is power 1, the fourth derivative power 2, sixth derivative power 3. So therefore, for f of 2r, because we're looking at only the even powers, remember, then this must be equal to negative 4 to the power r. So our general term, the top here, f to the power r, there always f to the power 2r, so we're going to have negative 4 to the power r, and then we're dividing that therefore by the factorial, which is 2r factorial, and that will be x to the power 2r. So the way we get the even powers only is to have an expression for 2r. The factorial is therefore 2r factorial, and the power from the work we've done in the table there is negative 4 to the power r. So the general term is negative 4 to the power r over 2r factorial x to the power 2r. So in general, what we need to do then is to evaluate the derivatives of the function and then look at those values when those derivatives are evaluated at x equal to 0. Substituting those into the general formula gives us either a certain number of terms, if that's what we've been asked to do, the first 3 terms, or possibly being asked to work out an expression for the rth term, i.e. a general term. The fact that cos 2x was all even powers of x shouldn't really be a surprise, because we know that cos is an even function, and therefore its polynomial approximation is going to be made up of just even powers of x. Here's the approximation up to x to the power 6. So you can see there we have negative 4 to the power 3 in our expression there, divided by 6 factorial and multiplied by x to the power 6. And you can see how good the approximation is, close to x equal to 0. So it's already very, very close in the range from negative pi by 2 up to pi by 2. But we can keep increasing that, so the next one would be x to the power 8. And now it's almost exact in that range from negative pi by 2 to pi by 2. And that's the end of this particular video. In the next one we'll be looking at the application of Maclaurin's theories to limits.